I would like to introduce Omar Baldonado, who will be presenting AI Data Center Networking Lessons from Meta's Evolution. Omar leads the groups that develop and operate Meta's global data center networks. Omar has been in networking since the early 1990s. I was not even born. And it's a pleasure to have him speaking with us today. Welcome, Omar.
All right. Thanks. Hi, everyone. Excited to be here, and this is a really exciting event for me personally because dating me to the early '90s, right? I've been in networking and seen a lot of the growth, as many as you all have, and it's particularly an honor to represent a lot of the work that our teams have been doing. And hopefully, here at the end, engage in some questions, and I really want it to be get some feedback and get into it here at the end. So I'm going to go through some of our journey so far. As we said, that I'm part of the infrastructure team at Meta. We run the network infrastructure, and in particular, I focus on the data center. There's the backbone network. There's really we're a global network overall. And we'll see increasingly that is all in service of our AI needs. So let's go a little bit about the AI context. It's not too much of a surprise, but I'm going to go over it here, especially from a Meta perspective, so you get a sense, right? This is our current number of folks that actively use some sort of Meta product, whether WhatsApp or even Meta AI, Instagram. 3.5 billion users daily. And the number of messages that go across is staggering, right? So if you look at 3.4 billion dailies, what does that mean from a network perspective, right? This is not an AI flow. This is a regular sort of web flow. But pretty much every arrow is a network connection, right? So that 3.5 billion comes in, and it just explodes out into lots of communication all across the infrastructure, which I think network operators and folks tied to network would know. So related to the AI, Meta AI itself has now more than a billion monthly active users, right? Whether it's within the core products or the wearables, right? Like I've got the new display glasses here. I'm going to take them off in a little bit, right? Because this is tied. I can see messages from my son or my family right now, and I'm not going to answer them during the talk. But just to give you a sense, like more and more I depend upon these. I go on a walk with my dog in the morning. This is one of my primary use cases, and I get a personalized podcast. I can say, tell me about the thing, some topic, and I can go for a few minutes, and it tells me, and I interrupt it. And I say, wait a minute, tell me a little bit more about that. And all of a sudden, my half-hour walk with my dog is all done because I've just been kind of learning and doing all this. So more and more AI will be pervasive, not just within the apps in our phone, but in everything that we do. So a little bit about, again, this is just context setting, just to give everyone here a sense of just how fast everything in AI has moved. Right? So the Turing test, which I think everyone knows about, but we have well answered that. I think now can a computer actually fool you into being a human? I think that happens all the time now. But if you look at how quickly, or not quickly, actually, it took a long time here to get from that test to say Deep Blue beating the world champion in chess, right? 50 years. Then from Deep Blue, end of the 90s, up until the launch of ChatGPT, that was 25 years. And you can see a lot of the advances in AI technology happened in the last couple of decades. Since that launch, there's been this explosion for the last 3 years in models, in workloads, and it's really caused the takeoff, right? So from 50 years to 25 years to the last 3 years, and here we are, beginning of 26, right? So that's the context. The rest of the time I'm going to spend talking about why I believe this is a great time to be a network engineer. Right? So I'm just going to take these off now so that I don't get the messages. So the first part is there is so much technology for all of us to learn, right? It is an end-to-end problem. It's a full stack problem. So I'm going to go here into the physical infrastructure, again using Meta as an example. Just to pause a little bit here. This is Nanog, so I'm assuming there are a lot of network operators here. Can you raise your hand who has actively either run in the past or is currently running a network? Okay, it's good. This is actually when we go to other venues, this is like the most dense operator group, in terms of number of hands. Other folks here, I'm guessing vendors. Is that right? Let's see. So yeah, different. One of the big takeaways that lessons here is that the operators need to work super closely with the vendors, more so than ever with AI, because of this full stack end-to-end problem, right? So let's go over it. So if I start at the global level, right, Meta's infrastructure has thousands of locations, couple hundred countries around the world. This is for our caching and edge presence. Then in terms of, as a global ISP, we have hundreds of thousands of kilometers of subsea fiber as well as terrestrial fiber. One of the things that recently closed here that we're very proud of is the 2 Africa project, which we announced several years ago, completed the core infrastructure of it end of last year. And so this connects dozens of countries together. It brings a lot more bandwidth to really 40% of the world's population. Again, we build this for really the internet infrastructure as a whole, and a lot of it is to better serve AI, better serve the users, and just give them the bandwidth they need. And then again, last part on the global infrastructure perspective, we've now announced this Waterworth cable, which is even longer than 2 Africa. It will be the longest subsea cable in the world, connecting pretty much all the major continents, and again, providing diverse paths, more connectivity to all of the world that that's using AI and using all of our applications. Okay, so that's the global perspective. Now, if I zoom in a bit to the regional perspective, right? These are the sizes of the clusters that we've been working at Meta that are dedicated to AI. And in particular, large-scale AI training, which I'll get into a little bit in terms of how that's been changing as well. You can see here, 2020 to 2023, we spent a lot of time just kind of building up the clusters up until these 24K clusters. The 24K clusters are what we trained an earlier version of Llama, and we had two 24K GPU clusters. Then after that, we built the 129K GPU cluster, and that was used for initial versions of Llama 4. We built that in 2024. Right? And then you can see how this is progressing. We have dozens of data center regions around the world. Most of them are in North America, but then you can also see an expanding presence there. One of the things with AI that we've talked about is the amount of power that's required. And we announced two of our multi-gigawatt locations, Prometheus and Hyperion. And just recently, we announced the energy partnerships that we've been working on to support this large-scale build-outs. Right? So very excited about the various forms of energy that we're investing in particular some of the clean energy is the nuclear energy that we're doing here. Now a little bit more on the networking in these regions. When we look at something like our gigawatt clusters, it's easiest if it's a greenfield, right? You're going to build a huge campus with lots of buildings all networked together. But sometimes as we all know, it's not greenfield. Most of the time, it's not greenfield, it's brownfield. So you have to go into a place with different locations and then connect them up. So this is the trenching that's going on of outside plant fiber in our Prometheus cluster. And there are millions of kilometers going on here just because of the density of what we're trying to connect between the buildings. And in fact, a recent announcement that we went through was just last week. I think we announced this deal with Corning in terms of securing the amount of fiber that we have to work with. Right? I'll get to the lessons a little bit more coming up, but hopefully this gives you a sense. We went from global to regional, and a lot of those global obviously has its realities of geography and distances that you have to deal with as a network engineer. Regional, you have to deal with things like space and power and fiber, especially at the higher densities. Now, zooming in inside of a building, this is hopefully a little bit more familiar to you all in terms of when you build fabrics inside the buildings. We're going to talk about scale-out fabrics inside the buildings, and that's where a lot of the GPUs connect in and need to kind of have their very high bandwidth, high performance networking. And so we've built a couple of different generations of fabrics. We've shared these in other venues like Open Compute. This particular one is something called a disaggregated scheduled fabric. And essentially we know if you've worked with chassis before, router backplanes and router chassis, we took the scheduling that happens between those cards in a chassis, took that algorithm and ran it across really a whole building in order to get all the GPUs hooked up effectively to what is a giant 20,000 port router. One of the advantages of this is it handles a lot of different types of accelerators and NICs, and then you can compose these into even larger cluster sizes. More recently, we announced a non-scheduled fabric. This requires more tuning because you don't have, you just assume router backplane scheduling works like it does in DSF. But now when you're not scheduling it, you have to be much more aware of the whole network problem and how you're tuning from the NICs and the applications through the fabrics and making sure that works. This is actually we've tuned to handle some of our largest AI cluster builds. So that's a little bit about the fabrics. Scale out, more on its way. We're looking at, there's so much networking going on. We're looking at, we've talked about, people have seen like liquid cooled AI systems. It's big enough now we have liquid cooled network systems. So again, so much technology to be exposed to and learn. All right, so we went from the global to the regional to the building. Now let's get inside the rack, right? The rack is where, from an AI perspective, the AI systems run. Most recently, there's, as you've been tracking, there's the NVIDIA GB200 and GB300 systems that are rack scale, and more coming from AMD and other companies that are building really rack scale systems. There is a lot of networking in here. You can see, you can just see the cables. Actually, sometimes pictures show up and they don't show the cables. I personally take offense to that. I'm like, wait, you got to show the networking. You got to show the purple or the blue or the black. You got to show it all, right? Because that's where the networking is. So there's a lot of networking in these rack scale systems. It's the domain of scale-up fabrics, right? Very, very high performance. They're really at the leading edge of what are the optics or the SerDes or just generally the bandwidth coming that can be driven by GPUs. This is very high performance, high density. Some of our work recently there, we work very closely on the NVLink technologies, but then also we're working on using Ethernet for that scale-up fabric inside a rack. All right, so zooming in even further, let's talk about the blades or the silicon. And again, hopefully you all get the sense, networking is in all of these places. This is part of what is so exciting. networking down at the chip layer, right? This is, sometimes people call it the scale-in network, but how fast are the chips able to talk to each other, die-to-die interconnect? What is the speed of the chip and memory, right? Do I disaggregate the memory? And what's the latency of that, right? So the design of the chips itself is very, very dependent on networking. So this is our own meta roadmap for our chips, training and inference, and different types of accelerators there. So that kind of brought us all the way through from the global to the ASIC level. Just wanted one lesson here. It is not. It looks clean, like, oh, things get bigger, and this is just how things progress. Double, 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 double. I'll tell you, one of the learnings from as I was talking to our teams, they said it is not linear. There are so many restarts, pivots. Wait, we thought we were going to go with this, go with that. We tried that for a little bit, and now we move into something else. I don't think it's quite as chaotic as it was in 2020, 23. From a controller and a routing and a ECMP design perspective, we must have run through half a dozen versions of topologies in that 2020 to 2023 period. It's a little bit more stable now, but still there's a lot to keep up with, because the things that drive the innovation, what drives the cycle now, is how fast can you keep up with the GPUs or the accelerators. They're pushing to put new product out every year. Multiple companies are doing that. And so how do you keep track of that? And so that's why you want to stay plugged into the AI roadmaps, and then find out how networking matches that. And that's, again, one of the reasons why it's a great time to be a network engineer, because of this whole tied to all of this whole stack of technology. So if I look at that stack, right, this was actually something that we went through from just a scale numbers. It was boggling, right? We talk about chips at the nanometer scale, but then we're also talking about millions of kilometers. Right? I don't know if no one talks about what's a million kilometers. So one order is a megameter. It's a gigameter. We have gigameters, but we don't talk about gigameters. But we're talking about a huge number of a huge range of distances. We talk about power optimization within the chip, but also within the building, is an important constraint for infrastructure designers, but also the network is a part of that infrastructure. We have to understand what power is being taken up by the switches, the optics or the connections, the NICs. They all factor into this power. So again, going from chip level, say picojoules per bit, all the way up to the gigawatts. And then finally, from a performance perspective, it isn't so unreasonable for us to look at getting to zettaflops or even yottaflops. I had to go look up. I was like, wait, let me make sure. But if you look at an H100 GPU, roughly, depending upon the accuracy, FP4, FP8, you're talking about a petaflop. If you have 1 million H100s, that takes you to exazettaflop, right? And then with each generation of improvement, let's say, between H100 and GB200, there was an order of magnitude improvement. So then you look at the chips themselves, let's say over 3 generations, getting 3 orders of magnitude faster, and then you're into this yottaflop regime, right? So again, networking folks have to embrace all this. This is amazing, right? So that's the first lesson, and why I think it's exciting. There is so much for all of us to learn together, right? One piece of advice: don't learn just one layer or one component, right? I'm the fabric person that really knows this fabric, or I'm the optics person. I really know optics, FR4, ZR4, DR4. because these all have to work together, it behooves all of us, all of you, to understand different parts of the stack, end to end and up and down. That gets into the software side also. I haven't gone over the software yet. I'll go into that. That's why I think this is the second reason why I think it's great to be a network engineer. Network engineers have always been the ones that pull it together from an end-to-end solution. So if I look back, and again, thank you for for dating myself. I remember when one of the network engineers I worked with in the 90s, Sean Finn, and he came and he said, like, I've got this network general sniffer. I'm sort of curious who's used a network general sniffer. It should be a little smaller group. I've got this network general sniffer, and there's this port 80 stuff. Thank you for raising your hand. So there's this port 80 stuff going on. We got, it's showing up. We got to learn about it. Okay. So we started, okay, what web? Okay, what's the sort of technology going on there? So as network engineers, we had to kind of like, hey, what's the application trying to do there? And then of course the 90s saw, okay, now we're doing online, e-trading. We're doing all this stuff on the web. So we learned about that application, right? Look at the next one, streaming, right? I remember working with folks early 2000s trying to understand this MP3 streaming. There was a company, Real Networks. We were trying to like, what this is pre-YouTube, right? Pre-YouTube, and like, okay, what is that? Right? And so then we all started learning about playback buffers and jitter sensitivity and loss, right? So to make the network work for the application, we all learned about that, right? Why was jitter important? And we all felt it at the time when our videos would freeze. We still feel it, by the way, it's always the network. But that's when we really learned about this sort of real-time video and real-time streaming and the performance that the network can provide and how it impacts the application. So here we are today. I mean, I can go through the different technologies. Mobile phones, iPhone, that was also another, had implications to network engineering and design. But now here we are with AI, and that's what, again, just like we did it for the port 80 that we were seeing on the sniffers, just like we did it for streaming, we have to bring these various components together and make it work for AI. Right? The role of networking for AI, it seems so obvious. But a lot of folks, when we think about AI models and a lot of the research, just for ease, people normally think of having one GPU. They can train a model on one GPU. They can serve a model on one GPU. And that's where a lot of people have started, because most people don't have access to very large GPU clusters. Right? We throw the numbers up, 128 GPUs, those are big numbers. Like most people don't have access to that many GPUs. But once you start leaving a GPU, one, you hit the network. Now a lot of it is hidden inside the system. Say with the H100 systems, you had 8 GPUs that was kind of hidden in there. But once you start breaking out into the rack, that is where network engineers play. And that's where we're critical. Let's go over a little bit about the software. Again, I'm not going to go into a lot of too much detail here, but it's trying to give you the same analogy. Just like we learned about jitter and playback buffers, just like we learned about how many turns does it take to do an SSL authentication, and can I reduce those number of turns so that I have faster web connectivity. Learning about the AI application and how it's trying to leverage the network helps us do a better job in supporting the application. So one of the techniques I mentioned, when you talk about multiple GPUs, how they're going to talk to each other, there are different things that there are different ways that the model designers think of doing that, right? You don't want to multiply a row of them, you want to do one row of matrix multiplication. You don't want to do that over the WAN. just hopefully is obvious, because there's so many of those matrix multiplies. You want to do that in as fast, ideally you don't hit any of the fabrics as fast as possible. And that's called tensor parallel, right? And so when you work with model designers, and this is something that a lot of our network engineers learned over the last few years, the model designers are used to working on one GPU or working in one system. I mean, this is 4 or 5 years ago, but now I think most model designers know, hey, there's a network. But they want to understand, they need to know, and we can engage with them like, hey, this type of operation you're trying to do, let's say a fundamental matrix multiply, there's speed of light. I shouldn't do that over the WAN, so let's do this way in this part of the network. And then the other parallelisms that the models try to do, let's say data parallel. It's basically sharding of the model, the data that the model can be trained on. That I can do over longer distances, across scale out, or even the WAN, from a fabric perspective. So understanding and being the representative of the network, the capabilities of the network, this is the type of networking I can do within rack, within building, between buildings, and let's work together on how to make that scale and work well for models. That's the role of a networking engineer. And not all models are alike, right? I think not all models are alike, that's right, but not all workloads, not all AI workloads are the same. So you look at training, we talk about training, so many flavors of training. Training for a large language model is different than training for ranking and recommendation, R&R, right? Training, there's also the world of like a large foundational model training, and then there's post-training, kind of where you're really trying to optimize the model on a particular use case, like coding or image recognition. And then inference itself is somewhat dependent on the model, right? If your inference model if the model you're trying to serve up is so big that it doesn't fit on one GPU system, you may want to break it up, right? So now one stage of inference, pre-code, may be on one set of servers, and then the decode part of inference is on a different set of servers. Now, there's a lot here, and that you may not know, depending upon your exposure to all this, it takes some time to kind of understand the different models and workloads and requirements. But again, this is something that we have to do, because the network is fundamental in this. If I look at the dimensions right here in this graph, right? I haven't explained the graph here. Just kind of for the different types of workloads, what is most important to them? So prefill, you can see the orange, is very compute intensive. Right? If prefill, just a quick prefill decode, prefill is like, I'm trying to think of what I'm going to respond. So I take some time to think. Then decode is, I'm going to tell you what I just thought about, right? So when you ask somebody a question, like they may sit there a little bit, think, and then they tell you the answer, and hopefully they're not pausing in between the answer, they're just letting it come out, right? So the compute part of inference, the prefill part of inference, compute, is very compute intensive. The decode, which is the red, you can see network latency sensitivity. Right, so because you don't want the jitter or you don't want the pauses in the speaking, in the response being served up to you. You want it to be just very smooth and coming out as quickly as possible. Right, so this is the translation. Sometimes people talk about like time to first token as a model evaluation criteria. How quickly can you get that first token is really like a compute problem, and then or a prefill problem. How do you serve that up is a decode problem. And again, this reminds me again of all those other times, like, oh my gosh, I got to learn about streaming. I'm going to get to learn about web. This is what you get to learn now as a network engineer. And there's a lot more. Actually, that graph doesn't have, I just throw up a couple of models. There's mixture of experts, which implies a different sort of parallelism that you can do on expert parallelism on the infrastructure. There's reinforcement learning. Reinforcement learning has a whole bunch of servers talking to each other, and more like a traditional distributed system, right? There's even work that's going on at the software layer to say, go and make sure that the traffic between the GPU and CPU are minimized, right? So in a traditional AI system, there's a lot of coordination between the CPU and GPU, because the CPU kind of does all the planning, and then it kind of sets it up for the GPU to just go compute very fast. But it introduces extra turns between the CPU and the GPU, and reducing the number of turns, or reducing that communication and just having it being very GPU centric increases efficiency, right? And again, I alluded to it earlier. It reminds me of when we were trying to do some of the SSL handshake work, again in networking, when you're trying to do, this is now internet distances and latencies. If you're in a part of Asia and you're connecting to a data center across an ocean, every round trip in a handshake for, let's say, SSL is expensive. So you want to reduce those turns. Again, network engineers familiar with that. This is the same problem, right? It's just it's happening in a much smaller context, and it's happening, millions of times during a workload, but it's trying to optimize the CPU to GPU communication, or minimize it, right? Again, from there's ways to get involved here at the software layer. We announced some of our library work with PyTorch to provide a more scalable and flexible framework for this GPU to GPU communication. And actually, we open sourced a lot of it. One of the things I'm really proud of, and the team, I think, excites the team to be able to share our work. We've shared how we've made Rocky scale over the last several years. We're sharing how at the software layer and we've even open sourced some of the code in terms of what needs to happen to make 100,000 plus GPU cluster work, right? Last thing in terms of some of the more software, then I'll get to this integration part. Just wanted to map LLM, because there's a lot of different pieces we're talking about. What does it mean for an LLM to work on the infrastructure, right? So just trying to break it down, right? Pre and post training of Llama 4 happened on the 129,000 cluster, and now it's happening on GB200 clusters in our gigawatt cluster. And so that pre and post training happens. There's a lot of capacity there. It's all running on Ethernet, Rocky. But again, that's the training part, different stages of training. Inference happens because we have this billion active users for ourselves, but everyone's trying to serve it up as quickly and as broadly as possible. Inference happens on not 129,000 machines, hopefully it doesn't require that. Inference happens on a small number of machines, either one machine or a couple of machines, because you want to really try to, that's where the numbers come, right? Training a model may take 120, a million GPUs, and they run for a month, but then you want to be serving a billion users just as fast as possible. And that's like a web scale latency workload that you really want to kind of watch. And that's kind of the serving inference part of it. And we use what's good for large scale training may not be good for inference, but you want to kind of have fungibility so that you're not totally committing your infrastructure to just one. This chip or this cluster is only good for this, but you have to then be aware of what can this cluster do. Okay. So that's networking pulls it together, right? Network engineers pull it together. The technologies have to work, so you have to understand the performance of the application. Then operationally, you have to debug it, right? You have to run it. Is it the network? Common question, right? If you look at, again, falling back at the model developers, they'll say like, look, when I'm programming, there's a very clear fork in the PyTorch, in the model code. Am I talking to a local GPU, or am I talking not to a local GPU? That's it, right? And so anything that happens to talking to not a local GPU looks like a network problem. So it's like, I'm talking to my local GPU, all 100,000 or anything else that's happening looks like network. So we get this question a lot. is it a network? And we have to debug the components. There are millions of components in one of these large clusters, billions across the fleet. We have to work on auto-diagnosis, correlation techniques. So, and again, this is because of the application knowledge, that's what lets us do that, right, as a network engineer. Network engineers also, again, this slide is just to emphasize the non-greenfield nature of the problem. In this picture, there are 4 generations of buildings that are coming together into our gigawatt cluster, right? The H-style buildings are an older generation. The ones at the bottom are liquid-cooled facilities. So all those little dots in the bottom are cooling units that cool the buildings. So there's like closed-loop cooling that goes out. And then there's one of our sprung structures in here, kind of next to the middle H. There's a tent, which we had to stand up super quickly. And then the buildings at the far right are not our buildings, but ones that we've leased and have put our infrastructure inside. Heterogeneous. So when we talk about the Prometheus cluster, it is not purpose-built from the ground. It has multiple generations, and again, the networking is different in each one of these, and then we're trying to network them all together. Is a really good problem for us. No, it's a challenging problem. It's an intense problem. Okay, last thing. Why again do I think it's a great time? We can go faster with AI ourselves. I've been talking all this time about building the network for AI. This is now the AI for networking, right? How can we all go faster? So at previous Nanog talks, some of my Meta colleagues have talked about how we automated away our NOC. We don't have a NOC. We figured out the thresholds and rules. We wrote code to detect anomalies, take automatic correction, right? We've also automated some of the config generation, through intent-based networking, and then there's a whole system to push and go update. But in both of those cases, we had to write a lot of software. And so network engineers were paired up with software developer teams. Now, the network engineers wrote a lot of software. Perl, Python, Go, C++, everyone's writing a lot of software, right? But certain systems, you had to pair up, and there was a dependency with software engineers. Even if I want a dashboard, I had to go talk to a React UI person to kind of build me a cool dashboard that I want, right? But in this AI era, companies can quickly develop the software that we need. I've talked to a number of operating companies to say, how do we kind of go faster with software development? And one of the blockers in the past has been, we don't have a large software team. You don't need a large software team for a lot of this. Some of this you do, but pair up network engineers, or network engineers can go just use the technologies themselves, go use an agent to help you, work with software engineers who are also using those same agents, and then just work through it. A lot of what I hear, sometimes somebody will go like, I asked the AI to generate a fabric and it didn't look good. You're like, oh, okay, not ready, right? Maybe it's ready for that coding stuff, or it's ready for whatever image generation, but it's not ready to generate my fabric definition, right? I get it. There's probably not a lot of training for network fabric generation, but work with it. Explain the rules that you have for how you want to write your fabric. Explain the rules for how you want to fix things and automatically remediate things, and kind of iterate with it. You can't one-shot it. Anyone who tries to one-shot a prompt with an LLM, you're almost always frustrated by that. But if you work with it, you can really get a lot of good results. And this is something that we've been doing internally. We haven't published some of that work yet, but it is definitely accelerating us. Right? So that sums it up, right? I think it is a great time to be a network engineer. Lots of technology. It leverages what we've been doing, kind of the natives, the skills that we have of pulling together solutions, and we can supercharge ourselves with AI. So I think I've got a few minutes. Thank you very much for listening, and hopefully we have a few minutes for questions. We've got mics if you've got questions, or you just yell it out and then I'll repeat it if anyone has a question. Oh, here we are. Thanks.
Hi, Ido Kadim from CPacket. You're from one of the few companies that really run inference at huge scale. And there's a lot of discussion about the design of clusters, but I'm really interested in how you see the network at the edge of the clusters, where all of these inference requests and needs come from all different places with all different characteristics that must have a unique network implication as well.
Yeah. So I think that is something that is coming, right? Because when you look at that global infrastructure we have, and that many companies have, right, you want to move as much of it as close to the end user as possible. That's why we have caches all over the world. We have POPs all over the world, and over time, more and more of that edge serving will push out to the edge. We'll get closer to the user. In some case, we look at it. Can we do it on the phone, right? But then if you can't do it on the phone, can you do that in a localized compute facility geographically? And that is definitely coming, and it is because of a fundamental networking problem there. Better to get to serve it up locally if possible. There is a lot of complication there too. Different countries have different rules about what data is hosted where, that sort of thing. But it is a networking problem that we'll get to, and we're working on. Oh, sorry. Yeah, we'll round robin here.
Yeah, actually, I have a question from remote. So this is from Daryl Newcomb, who's
okay, perfect.
Unaffiliated. The question is, if I understood correctly, with your description of DSF as being straightforward and performant, what are the top primary drivers for having used non-DCF in your largest footprint of clusters in a single region?
Okay, good. So just to recap there, so I mentioned a couple of scale-out fabric technologies, DSF, and a disaggregated scheduled fabric, and a non-scheduled fabric, right? The trade-offs, I think, there was the question, disaggregated scheduled fabric just looks like one big router to the application. And you don't worry about performance usually going into and out of a router. You rely on the backplane to work. But on the other hand, that does come with some overhead of scheduling to making sure, like, hey, that output port that's on the other side of the building, I can get a path and it's ready to serve this up. So there is a lot of scheduling that goes on, and that does have some impact on performance. So, but it has flexibility. So when we move to something like a non-scheduled fabric, there's a lot more work then to make sure the applications from the application layer through the NIC are properly tuned to work with a non-scheduled fabric. So that's the real choice around that. We have both, different use cases for both. But then when you talk about extending the scheduling across very long distances, then it becomes much harder to get that across between buildings or across longer distances. Thanks for the question. I think this is our last one here, probably.
Okay, thank you.
Okay.
Hi, I'm Meg from Marvell.
Oh yes, hey, good to see you.
Really engaging talk, and I have a lot of questions, but I think I only have time for one. So I was wondering if you can talk a little bit more about the decode for inference and the memory bandwidth requirements and how that may impact the network.
Right. So the question to decode for inference, I think, and again, this is why I think it's exciting for all of us in the room to understand, like, what does, that's a little bit like understanding why was the playback buffer different, why was it better in YouTube versus in this, or what, Netflix streaming uses TCP, but Google streaming uses Quick, UDP. So you're really getting into this deep understanding of what the application is trying to do. So decode specifically has a set of requirements in terms of making sure the latency is low enough. So whereas prefill has a much higher, say, memory requirements, right? So in a way, I would say it's not so much specialized just to decode, but it's more like what does a prefill server have to do that a decode server doesn't, right? And how much of the model needs to be available, how much of the data needs to be available for that precode step, and you can optimize it not to require that in decode, right? And so then you get into questions like, do I buy dedicated decode servers versus prefill servers? That's a very optimized problem for large-scale infrastructure. It may not be generally applicable, but I'm happy to get into it. But if you think like, I think what I see a lot of other companies doing right now, maybe depending on the size of their infrastructure, their question is like, do I get inference servers versus training servers, right? General GPU servers for training. Do I get more dedicated inference servers? That's probably where I see a lot of the infrastructure debates right now. Understanding also, though, that if you get things that are super optimized for inference and you need to shift around your infrastructure, if I need more training all of a sudden, I can't just move the training workloads onto those dedicated inference servers. So I think, happy to go into it more offline with you, but I think more general purpose, when you think about infrastructure, you're trying to weigh, am I getting the most out of the fastest performance, but then am I also getting a certain amount of optionality and fungibility? Because you don't want to just commit large amounts of infrastructure that can only do one thing. You're always trying to balance how much flexibility you need. So that trade-off may be different for different companies. And we can chat more afterwards. Thank you all very much. I'll be hanging out, happy to chat. Enjoy the rest of the time in Anand. Thanks for the invite and letting us talk here. And again, this is work on behalf of all the teams at Meta, many of them who are here today. So hopefully just connect with me or connect with them. We're happy to chat more. Thank you. Thanks.